Welcome to week 3 of our MAPS 362 3D modeling class. And now we're going to get into lasers. We're going to start talking about the principles of how lasers work and how we take measurements using them. This whole first is like week 3, but the introduction to LiDAR, I'm going to look at the general theory between both airborne and LiDAR, and then I really start getting into airborne LiDAR. So this week we're looking at how does a laser work, how does LiDAR take measurements, what are the components that we need to include when we're dealing with LiDAR, and then we're going to kind of wrap up starting more specifically into airborne. And then the next few weeks we're going to just look at airborne LiDAR and all the components that go into that, and then the last half of the class is all terrestrial. So we are done math. I'll let you know that. So we don't have any more hardcore modeling math to do. Everything that we do from now on is all going to be really looking at theory. So let's start with looking at technologies and what is included. So here's a brief outline of everything we're going to look at. So what is a laser scanner? And that's both airborne and terrestrial. We're also going to look at the methods of measurement that we use, the types of lasers that are out there, and then we're going to look at the components of a laser scanner, and then the basics of airborne laser scanning. So what is a laser scanner? So when I'm in class, I always ask, what do you think of when you hear laser scanner? And I get all kinds of stuff, right? Because some people have some experience with laser scanners. Some people don't have any experience. Some know of LiDAR. Some think of laser rays. So they're cutting through things. And yeah, there is a specific type of laser that does do cutting. You can cut metal with lasers. There's all kinds of information that comes from students. So really, when you think of this, there's lots and lots of stuff that comes from it, right? So what we're really specifically looking at is that we're capturing and recording geometry, and we're capturing and recording texture of anything that is a visible surface. So we are not looking to capture anything that we can't see with our own eyes. So going back to remote sensing and thinking about the electromagnetic spectrum, we're using the visible spectrum in laser scanning. Except we do go into optical, near infrared as well with airborne. So we do kind of cover a bit of a range there. We also, the end product of laser scanning is a 3D digital representation that we can do measurements that gives us values of our coordinates for every single point in that point cloud, and and then we can also measure with a certain, we can measure the accuracy based on measurement uncertainty as well. So this is really important to keep in mind when we are laser scanning, is that there's this measurement uncertainty that comes with it. Now, any technology has some sort of measurement uncertainty. You can think of laser scanners as being a total station on steroids. So some of the stuff that we talk about in this class actually plays into what a total station is working, what they deal with as well. So we have a bit of a definition of what a laser does. So there are many different ways of actually doing measurements with it. So we're looking at an optical 3D measurement. That's where it starts. It becomes a laser beam at that point, and we send it out. And I don't like the word shooting. So we don't shoot lasers. That's not what we do. And it drives me crazy when I read reports that you guys do, and it says the laser shoots out of the scanner. It doesn't do that. It is pulsed. Pulse is the word that we use. It is, or you can say that it is sent out, which is another way, or transmitted is another word. but we don't shoot lasers. That's just that you shoot guns, you don't shoot lasers. So optical 3D measurement, that's what we start with. We have two major categories that can fall in between the two. One is triangulation, the other one is speed and coherence of light, or speed and or coherence of light. Triangulation itself has it has two different kinds of measurements that need to be done for the same point, right, to be able to create that triangle. So we're looking at passive, we're looking at stereo imaging. And photogrammetry is exactly that, right? So we are triangulating between two images, and that is a passive form of triangulation, because we have two static images, we put them together, we create 3D. With the other type, which is active triangulation, what we're doing is sending information out to the target, and it reflects and it goes to another receiver, like separately. And so we're creating a triangle based on the transmitter and the receiver that is a part of the whole system. Those ones are a little bit more complicated to set up, but they are good for really close range stuff. And as long as you have a high measurement of angles and initial ranges, then you can do this triangulation. The other type of measurement is the speed and or coherence of light. So now that we're dealing with light, we are now looking at three different ways of measuring that, right? So the first one is the time of flight. This is what we call specifically a pulsed laser. And this is our C10 that we have for Leica. It sends out transmits that laser and then, or pulses it. So it sends out this pulse. We have like one blob of light that goes out. It interacts with the target. It scatters back to the scanner, and the scanner requires the time. And so from using that time of that range, it's going to tell you the distance to that point. The phase measurement techniques are like the P series or even the BLK 360. They use phase measurements. And this is where we're looking at fractions of phase. So like how much out of phase is the scent. So the scent, that's what I'm looking for. Let me try this again. So I'm recording this at like 9 o'clock in the morning and I'm still working on my coffee. So just to give you guys an idea of where I'm at right now. So the phase measurement, we're looking at the waves of the light and how much in and out of phase they are from each other. So I send out a phase that I measure and I know exactly because I set it. Like here's my phase that I'm sending out of my light in my beam. And then when it returns, there's going to be a shift of that wave. And so what I'm doing is measuring that shift to be able to get my distance to that object. Now, with that measurement and saying that, this works great, except the fact that we don't know how many waves have gone from the scanner to the object and back. We only know the fraction of which it is now out of phase. So that's one of the challenges with phase measurement. So oftentimes we will combine the time of flight with the phase measurement just to kind of get over that hump of ambiguity that we have with with how many wavelengths we have. The last one's interferometry. Obviously that's more on the microwave side than it is with lasers. And that is looking at phases as well, but it kind of expands it a little bit more into a more complex system. We won't go into interferometry, but that's looking at microwaves. And we talked a little bit about that last semester. So types of lasers. So there are 3 types of lasers in laser scanning. The time of flight is kind of our C10. So we have the big scanner, the C10. You guys will see videos about that later. And a lot of LiDAR, like airborne LiDAR, tends to be a time of flight because it can go further, right? So it has a longer range, and that's what's really important with the time of flight. is it does have, so it measures the time delay like I mentioned, and then really all it does is measures the light to and from a surface. So we're not concerned about the phase, we're not like, so the simplicity of the system is much higher. Phase measurements measures wavelengths and fractions of wavelengths. So it's, as I mentioned, it measures that like phase shift between the sent and the received, but we don't know the number of waves between the sensor and the surface. So we need to incorporate something else in order to help us solve for that, which normally we put in time of flight measurements within the phase measurement. The last one is triangulation, and that's using the laser that's transmits and receives, and the receiver is separate. We use cosine laws and triangles. Again, we do have some known distances that we do know. We do know some known angles. Therefore, then we can actually calculate the other information that we need from that point. Triangulation, like I said, is done for like really close range stuff and maybe like really long range stuff, not so much in the applications that we use. So you won't see a lot of triangulation laser scanning in your world, just because the setup is so much more complicated. So time of flight scanners. The whole idea is ranging, right? So we use a GPS, is the same idea. We look at time of flight to calculate that range. And so I'm going to pull back your GPS knowledge in this case. So everything that we do is like, it really uses ranging. Like total stations use ranging, EDMs use ranging, even like microwaves that I deal with, those all use ranging. So the only thing that's really different is the implementation, the performance, and why we use them, right? So a time of flight scanner, like we think about terrestrial, we've got the C10. And the C10 works great for big areas. If you are working in a small room, the C10 is terrible because it, like, you need to be like 1.5 meters away from it before it will even measure it, measure the return point, and it's a big scanner. So it takes up half the room anyways, right? And it's not really easy to maneuver around. Where the BLK, for example, is much smaller, much easier to move around. It is much lighter. But it can't cover a large area. Like if you're trying to cover like a gymnasium with a BLK system, it's not going to be as good as what the C10 could, or even the entire building, like covering a school or a warehouse, right? So C10 is good for like, so, and that C10 is that range, that time of flight scanner that we're looking at. So the range is measured by the time to and from, so it's total time, that's tau, we see in our little equation here. And divide by 2, because that tau is the total time from the send and to the receive. So we divide it by 2 because we're only going halfway. C is my speed of light, and N is the refractive index. We often just set it to 1.00025 for most atmospheric applications, and that would be for LiDAR. It's usually set to 1 for more local, like single room type BLK. Well, BLK is not time of flight, but but like for the smaller areas that we're working in. So when the refractive index is 1, we just assume that the atmosphere isn't changing that much within that area, where airborne it does. So that's where we will set this number at 1.00025. So this is just giving you a quick idea here. So we send the laser, it hits the target, it receives it, and it goes, the mirror uses it to put it to the receiver, and we get this range in between the two. So the cool thing about time of flight is that we can get multiple ranges. And this is something that you can't do with photogrammetry. So this is really, really important. I want you guys in your projects to make sure you mention this, because this is really the key to being able to identify features and extract features and classify. There's just so much we can do because of this property. So a single pulse, so one laser, can have up to 5 returns. So if we see here, we've got our airplane, send it out. So it sends it, this is the emission, and then it's going to get all this data. So we can see that the echoes are kind of in there within the canopy, and then it hits the ground, and it also is going to give me data back. So I'm going to see 2, for example, from each laser. Now here, if it hits the edge of this wall, like, or let's say looking here, we go down, it hits pavement, it bounces back up, I only get 1. But here, if it hits the edge of the wall, I'm going to see a little bit of that edge, and then I'm going to see the ground again, and that's going to return. So again, now I'm getting 2 returns. If I look at a single tree with like maybe some big branches, look at all the returns that I'm getting within that tree. So the multiple ranges is really, really beneficial for us to be able to understand, especially looking at forestry, even looking at crops and looking at, the health of the crops, because if it's like, very, let's say, hail damage, the type of echoes is going to change based on how that crop has been damaged. So airborne is built for doing multiple ranges. That's really why we use a lot of the airborne, especially like, let's look at power lines. Like power lines, it'll reflect off the power line and then it'll reflect off the ground. So we will see both the power line and the ground, so we can measure the distance between the ground and the power line. And that's really a big deal, because in photogrammetry you can't see the power lines at all. So this is really, really powerful to be able to do this multiple ranges. So terrestrial scanners don't really have that same capability, but there are some out there, and we call this as a full waveform scanner. If we're using a full waveform scanner, then we're going to have, obviously, this capability to be able to identify between different returns. But terrestrial scanners are more based on trying to get the accuracy of the location of the point. And that's what, so we don't tend to have a lot of like full waveform stuff. Software can determine different ranges only if the echoes are clearly separate. So, so how do we do that? How do we separate it? So there are 3 types of like range detections, and really separating out these waveforms. So peak detection is the simplest form. So what it does is, as it receives this energy, it says, oh, there's a peak here. So I'm going to identify that as at this peak, that is the range. That's the time that we are using to be able to identify that point. So really easy until you get into something like this, right? So I would have a peak here, I would have another peak here, I would have another peak there, another peak there, another peak there. So that is 1, 2, 3, 4, 5 peaks. Can we identify that? Yeah, for sure. That's no problem, right? That's easy. But what happens if this was a little bit flatter? Would it really be a peak? So as it kind of blend together a little bit, we end up with a much more difficult time with the peak detection. And what else was I going to say about peak detection? So the peak detection it's simple, but it's also not as accurate, and it does have difficulty identifying between peaks close together. The threshold or leading edge detection, this gives you an idea here. So it says, oh, look, it's starting to change its angle from 0 to actually going up as a return. So the leading edge of the peak is kind of that beginning of the wave, okay, of this return wave of intensity. So the leading edge picks up that. If you've worked in seismic, they talk about leading edge. That's done a little bit differently. So so just to be aware of that. And if you're interested in the seismic discussion, we can definitely talk about that in comments or discussions, because it is a different type of leading edge than what LiDAR deals with. So, and that's GPR is what seismic works with. And biomedical engineering as well, because that's what I get to learn. It took me a little while to wrap my head around the fact that leading edge is not this leading edge. But anyway, so leading edge here, as soon as the beginning of the wave or of this intensity starts increasing, then it says, hey, that this is the start of that point, right? So we're looking at the top of here, and it says, okay, now start saying that we've got an object. Say that is the return of the signal. So that's leading edge. Threshold is also another one. So we don't have an example of threshold here. But what threshold is it says, okay, as soon as the intensity changes at a certain angle. So I might say if it exceeds 30 degrees, then you will say that it is a return. So let's say, for example, this is at like 45, so it exceeds the 30. So it would say right here at this point is the beginning of the tree. Or down here, it didn't exceed that threshold yet. So here, the rest of them, I mean, this one looks like it's greater than 30, so we're good there. This one looks like it's greater than 30, so we would say at that point, at this beginning point, is when we are detecting and saying that is a return. So that is that's your threshold or leading edge. It is a little bit more accurate and a little bit easier to identify between the different types of returns. So again, looking at leading edge, you can see that this comes down, and as soon as it starts to go back up, that's when leading edge is identified. The problem with this is that it can be very, very noisy. So you can imagine if you have a lot of branches throughout here and it's hitting every single one, like if you have 25 branches, if you look at like an old poplar tree or something, and have a whole bunch of branches, it's going to be really, really noisy. So every single time that it picks up on a change, it's going to say, oh, that's a return. And that means that you may never actually make it down to the ground, which has the biggest return, right? So that's important to note with the leading edge. So it can be very noisy. So you really have to like set some thresholds. Not, and even if you're not using threshold detection, you still need to set something saying, okay, this is like as much as I can interpret at this point. Like in this, I'm trying to think of a good example for leading edge detection here. So I like using threshold because it's much more straightforward. You can say this particular angle says yes, it is going to be an actual detection, or you can say that once it reaches a certain intensity, you can also identify it, right? So this is considered the mean energy ratio in seismic. So that ties it to that. But I would take a threshold. My threshold would actually get into constant fraction. That's more of the mean energy ratio. But I could say, okay, I want, as soon as this exceeds maybe whatever this value is here, let's say 50. So as soon as it exceeds 50, then it will be an actual return. So we may end up cutting off some of these like this. The other challenge with this type is when you have slopes that are pointing away from your laser scanner. So for example, a roof. And if it is a steep roof, your laser beam has been elongated greatly. So once it's like being elongated into this long oval, then especially with threshold, it may never be a high peak, and it may not ever make it past the threshold of like a certain angle of the tangent of the returned intensity. So that can be a disadvantage as well. Then here we have constant fraction detection, And constant fraction detection, this is where I'm looking at that energy ratio. So you can see where it's like identifying different parts of the wave. And what this does is it takes both the intensity and, like I was mentioning before, the intensity and the leading edge, and it combines them into two. So it says, okay, at what angle does it meet this ratio? And so you can see with E here, so we have this wave here going from A to D to B. And so we have the peak. We have changes in the tangent of the curve. And then we have kind of another energy, which is showing maybe what, like, I'm not sure what, that one would be a measure of the ratio. So it's creating the ratio underneath. And where that ratio meets this wave, that's where we say E. So we're looking at intensity value, and we're looking at that angle, the tangent to the curve. And then once we combine the two of them, then we find this location. And once we can identify this location, then we can say, now this is a return. If this location or this ratio, this constant fraction, does not meet a particular threshold that you have set, then it will not identify the point. So it's a little bit more complicated, a little bit more math that's required, which when you think about how many points you have, it slows down the processing significantly when you bring in the raw data set. But it is the most accurate. So again, accuracy versus like time expense is always that trade-off. So the time of flight, range uncertainty. So range uncertainty, this is your distance. So what is my measurement uncertainty in the distance? Every measurement that we take, as you guys are aware, has some sort of uncertainty. They're never exactly correct. We can get close, but they're never exactly correct. So our time of flight scanners have an uncertainty between 5 to 10 millimeters, right? So this is kind of your like error bars in between. We can calculate the range uncertainty for every single data set by looking at the time rise in nanosecond. And so this is looking at the time. I didn't talk about that in the previous one, so let's go back here. What is a time rise? So the time rise is this leading edge, right? So when I say time rise, it is how long does it take for the start of the signal to the top of the peak to occur. So in this case, we go from -60 to 0. So that's in picoseconds. So we're going, that's 60 picoseconds. I think that's what P stands for, to get to that leading edge, or to get to the top of the peak. So that's time rise. So let's go back down. So TR is time rise in nanoseconds. So that would be in decimals, the previous one. Speed of light, C, always important. And then signal to noise ratio. So anybody who works in electrical engineering would be very familiar with signal to noise ratio. What that means is that it's a measure of how much noise am I receiving versus the actual signal that I'm receiving. And noise can be included in many different ways, especially with electronics. And we're dealing with a ton of electronics when we're dealing with LiDAR. So what is that ratio? This is often like listed in the metadata, or it can be calculated in the software. So you can get that data. It's not something that you make up. It's not something that I like hand you the number and say, here you go. So you can find it in your data sets. So once you've calculated that, you're going to end up with your uncertainty. And then usually, like I said, it's between about 5 to 10 millimeters for time of flight. And that's just the laser, right? So we're not talking about anything else that's included in the entire the entire system, just the laser. So phase measurement, moving into the next one, there are 3 major types that we look at. So there's continuous wave, there's phase-coded compression, and there's chaotic LiDAR. We're only going to look at continuous wave here. We're not going to look at phase-coded compression or chaotic LiDAR. Phase-coded compression is very similar to like GPS, right? So you know, we have a coded signal and that's sent down. You can kind of, it's a little bit easier to imagine with L-band, because L-band, which is GPS, it has a longer wavelength to be able to like put a message on. Visible light is so tiny that it's really hard to kind of imagine what's going on there. But there's all kinds of like sequencing and really some really interesting stuff that happens with phase-coded compression, but nothing that we are working with in this class deals with that. It's a much more expensive type of processing. And chaotic LiDAR is still in research mode. So in 20 years, you may see it hit industry, but it's not something that we're using right now in the real world. So in this class, we're looking at continuous, like I said. So we have a transmitter, we have a reflector, and we have a receiver, and we have this time travel goes across, and how much is this peak out of sync with this one? That's what we are trying to look at. So this web page here, number 8, if you go to my references, I do suggest taking a look at it. They've got really good information on phase measurement techniques. So my continuous wave modulation, we have 2 different kinds of modulation. We have amplitude modulation and we have frequency modulation. So you can see with my little GIF here, we have my signal that looks like that. And what I'm going to do is I'm going to modulate my amplitude. So here we can see every time it goes up, we have a large amplitude. When it goes down, we have a small amplitude. So that's what we mean by amplitude modulation. Frequency modulation, following this, so every time it goes up, we increase the frequency. Every time it goes down, we decrease the frequency. So what does this do? This allows us to say, hey, we are at this point on my signal. And so that allows us to measure with a higher accuracy what is happening with the laser. Well, that's why we modulate it. So we avoid measurements of short pulses by modulating this, so we can just send it out and we just let it run. So with the C10, you won't even notice that it's actually pulsing. But if you could see the BLK, because the light actually doesn't show up on anything, it is literally like a straight line, because it just continuously sends out that light and that information because it modulates it. So that's how it's identifying where on this signal wave it's using this. So it has a lot more waves in between in order to identify where it is on that signal. So what we're looking for is a difference between the waveforms, so the incident and reflected, and that tells us the time delay between the two. But because we can't identify how many wavelengths happen between the target and the sensor, because the light's just constantly being sent out, so we can't just use pure phase measurement. We do have to include some sort of time of flight just to be able to kind of get rid of that ambiguity. So measurement uncertainty, I'm just going to look at AM in this case. It's much simpler to calculate than FM, and you don't need to memorize any of these formulas because you can look them up if you need them. And again, you're not going to be doing any of this math, just merely, but you can if you like. So if you have the information for your project, you're certainly welcome to calculate these. Say this is what the uncertainty is based on the wave, and this is the uncertainty that I'm getting at the end. So this one, you can see that the speed of light is not an issue, but we look at the amplitude modulation wavelength, and then we look at the signal to noise. So those are the 2 acting factors when it comes to causing error. You can see here too that the higher the amplitude modulation wavelength, the higher the uncertainty is going to be. And then of course, the higher the signal to noise ratio, the lower this is going to be, right? Because signal to noise, so the signal should be higher than the noise. So I'm going to going to stop the video here, and I'm going to break this up into a couple videos just because I'm already at 35 minutes and I've probably lost your guys' attention. So I will stop this video and I will make part 2 as a second video.